Today, a very warm welcome to Katrina. Thank you very much for joining us. And over to you, Katrina. I'm now going to stop sharing. Thank you, Katrina.
Thanks, Mario. So I'll just share my screen and just wait for it to load. Okay, there we go. So as Mario has said, my topic this morning is my breed has single-step EBVs. Now what? So I'm a technical officer based at ABRI in Armidale in New South Wales. And my role is to producers using breed plan and related genetic technologies. So a very similar role to what LRF deliver across Southern Africa. So what I'm going to talk about this morning is an introduction to single-step breed plan, then go through the benefits of single-step breed plan, talk about what you can expect when your breed has a single-step breed plan evaluation, a couple of considerations when you, if you have already or when you do in the future, go to a single-step breed plan analysis. So is performance recording still important? And also some considerations around which animals you might like to genotype. And then a little bit on future directions and where we see things going moving forward. So to start with, I just wanted to go right back to basics and just talk about DNA, genome, genomics. These are words that people like myself use quite a lot, quite commonly, but are not necessarily well defined to the wider audience. So you may have heard DNA referred to as the blueprint of life, and that's because it codes for all of the different functions that the animal has. And when we talk about the genome, what we're really talking about is all of an animal's DNA. So we have an organism, in this case, a bull. That animal is made up of cells, and within the cells, we have a nucleus, which is where we find the chromosomes, and they're the DNA. So we're drilling down and looking at the DNA level for the animals. And so what we've seen in recent years is that beef producers now have the ability to take a sample from an animal, and you can send that to a commercial genotyping lab and get a DNA test done. Now, certainly here in Australia, we have 3 types of samples that beef producers are commonly collecting. There are some pros and cons for all of them. We used to do a lot of blood work back in the past and collect blood samples, but now the 3 most common samples that we see being collected are tissue samples. So that's where the animal has an ear notch or an earplug sample done, often done in conjunction with tagging. It's a nice type of sample because it can be done from birth, but it does require a specialized applicator gun like you see in the picture here, and also the purchase of these TSU tubes to put the tissue sample in. And another con is that we're not able to store these at home, so they are good for sending straight to the lab, but they're not good for you if you are looking to have a backup sample stored at home on your own property. We also see hair as a common sampling method, and most people will be pulling approximately 40 tail hairs from the tail switch of the animal, and it's really important if you are doing hair sampling to be aware that they need to be pulled, not cut, because the DNA is contained in the root bulb of the DNA of the hair. These are suitable for long-term storage at room temperature in a home environment, so we often recommend these as a backup sample. But the downside is that the genotyping labs are not recommending that they're collected on calves younger than 60 days of age. So you have to wait till the animal's a little bit older. And the third sample type we're seeing is semen through a semen straw. They obviously can only be collected on mature bulls, but where we see them being particularly useful is where you've got an animal that's physically unavailable, whether or not it's overseas or it's already deceased. A semen straw is a nice way to be able to get a genetic sample of that animal and still get your DNA genotyping done. So a variety of options. I'm not sure what the favoured samples are across Southern Africa, but I would recommend when you are looking to collect samples for DNA testing purposes that you make sure that you know what your genotyping lab's protocol is, and you make sure that you follow the protocol, their collection, storage, and mailing protocol for that particular genotyping lab, because they'll have the types of conditions that they want to receive those samples in. So we've got the ability to collect samples and send them away for DNA testing. And there's 4 major applications that you would be doing for doing your DNA testing for. Parentage verification is the first one. Management of genetic conditions. Pompey's is a good example of a genetic condition. That is not a Pompey's calf on the screen. That's just a random genetic condition picture that I found. But management of genetic conditions within the herd. Also management of qualitative traits. So this is things like coat color, red and black coat color as the base colors, and also things like horn or poll testing. And then lastly, the use in genetic evaluation, such as single-step breed plan. So that's what I'm going to talk about this morning. And of course, it's important to note that many producers will do a DNA test for a combination of the above reasons. It's not often clear cut that you're doing one of those things. You're often trying to do 3 or 4 of those things from that individual DNA sample. So it's perfectly valid to see a multitude of reasons to be doing genetic testing on your cattle. But as I said, I'm going to focus in on single-step breed plan. And so at the moment, we have 17 single-step breed plan analyses that we run here at ABRI. The first of these was implemented back in 2017, and we have 3 single-step breed plan analyses that include breeds across Southern Africa. So the first of those is for Hereford. That is a joint evaluation between Herefords Australia, New Zealand Hereford Association, and the Hereford Cattle Breeders Society of Namibia. And it's been around for a few years. It was first implemented in October 2017. And then late last year, we also implemented 2 more single-step breed plan evaluations that are, applicable for Southern Africa. The first of those being for Brahman. So that is a joint evaluation between Brahman Cattle Breeders Society of Namibia, the Brahman Cattle Breeders Society of South Africa, and also Brahman breeders that are recording with the Zimbabwe Herd Book. And then our third evaluation that is applicable for Southern Africa is Limousin, and that is a joint evaluation between the Australian Limousin Breeders Society, the Limousin Cattle Breeders Society of Namibia, and the Limousin Cattle Breeders Society of South Africa. So three breeds across Southern Africa that are utilising currently single-step breed plan technology. And there are, one of ABRI's goals moving forward is to work with our breed plan clients, those that are running breed plan evaluations, and try and move more breeds across to single-step breed plan. So I've said single-step breed plan a lot this morning. So what is single-step breed plan? What we're doing with single-step breed plan is using genomic or DNA information in the calculation of EBVs. And we're doing that alongside pedigree and performance information. So your conventional breed plan analysis, your non-single-step analysis, we use pedigree and performance information, both on the animal itself and related individuals. So siblings, parents, grandparents, progeny, grandprogeny, etc. All of that pedigree and that performance information is used to calculate the breed plan EBVs. With single-step breed plan, we have an additional source of information. We use the pedigree and the performance information alongside the DNA or the genomic information to get those breed plan EBVs calculated. So really, what we're doing is having an additional source of information for the breed plan evaluation to use. So in order for us to do that, we need what we call a reference population, and that is animals with both phenotypes, so performance data, The traits that you will collect on an animal over its lifetime, and genomics or DNA. They need to have both of those things to be part of the reference population. And it's really important that that reference population is representative of the population as a whole. And so that's why if anyone's been involved in discussions about what size reference we need, that we can't give you a straight answer of we need X number of animals, because it's actually more important that we get the composition of the reference population correct rather than having a set number. We need to represent the breed as a whole. And that's particularly challenging in breeds with diverse or composite backgrounds. So, for example, here in Australia, we do have Simmental breed plan evaluation, which now has single-step breed plan, but that was challenging because in addition to the traditional Simmental animal, like you see on the screen here, Simmental in Australia has a lot of black Simmentals with Angus influence, and so we needed to make sure that we had representation for both of those different types. I'm not sure how much black Simmental you have over in Southern Africa in the Simmentala breeds, but that's certainly a breed where if there is both the traditional and the black Simmentala, that it will be more challenging in terms of representing the diversity of the breed. And the other example I have here is animals with breeds with composite backgrounds. So, for example, here on the screen, I've got an Australian Brangus animal, and that is a breed we have got single step for now, but it was also more challenging in that we've got the Angus and the Brahman background coming together to form a composite Brangus breed. And so it's really critical for composite breeds like that we represent from the Angus across to the Brahman and get not just the F1s, those that are 50-50, but the breadth of genetic difference and genetic variation found within that breed. So it can be challenging to get there, particularly in certain breeds where there is diversity and there is composite backgrounds. But that's what we're looking for when we are trying to switch across to single-step breed plan, is to have the most representative reference population for the breed that we can. And so once we've set up a single-step breed plan evaluation, then what single-step breed plan is really about is relationships. So I've got a pedigree on the screen here. I've got a dad and a mum, and then their progeny. So this is myself and my brother. And so if we think about human height, I've got the heights there of my dad and my mum, and we can see that one is 166 centimetres tall, and my mum is 164 centimetres tall. And so if we were just thinking, right, well, what should the children be? How tall should they be? We'd say, well, mid-parent is 165 centimetres. And that, just to disclaim, is obviously assuming that all variation is genetic in height and that there's no difference between the sexes, which we know isn't true, but we're just going to roll with that for our example on the screen. But really, when we look at my brother and I, we see that we're very different heights. So I'm a bit shorter than my parents. My brother is quite a bit taller than me. He likes to use my head as his elbow rest. So we're seeing variation there in the siblings. Why the difference? Why haven't we come out the same height? It's because while we get 50% of our DNA from our mum and 50% of our DNA from our dad, each sibling doesn't get the same 50% from each parent, and therefore the assumption that we share 25% of our DNA with each of our 4 grandparents is likely not true. If we go back and look at my brother and I, here's our parents and our grandparents, the generation before, and if you think about which grandparents we are more likely to be closely related to, it's quite likely that I share more DNA with our paternal grandmother, who was also quite short. And my brother looks quite a lot like my mother's grandfather, so my mother's father, so our maternal grandfather, and it's likely that he probably shares more DNA with our maternal grandfather. So if you think about your own siblings, your own family, you're going to see certain traits that you throw back to certain people in your family tree, and that you don't necessarily look identical to your siblings. So we can see that in humans. We see exactly the same thing happen in cattle. So this is an example I've got here of birth weight, and we can see in this particular pedigree, mid-parent is plus 3.9, but we've got quite a bit of variation between these siblings. This one's plus 1.7, this one's plus 5.2. It's likely that this animal goes back more to this side of the pedigree, and this animal goes back more to this side of the pedigree. And the same if we look at this intramuscular fat pedigree. This example, mid-parent 1.7, this sibling 1.3%, this full sibling 2.8%. This one's probably going back more to that side of the family, and this one's probably going back more to that side of the family. And so that's what single-step breed plan is doing. It's looking at the DNA level, and it's taking account of the animal's actual genetic relationship with all of the other genotyped animals. And so in a conventional breed plan analysis where we don't have genomics, we don't have the DNA information, we assume that you get 25% of your DNA from each grandparent, but actually we know that that's not true. How much you get from each grandparent can vary. It might be as little as 20% for one grandparent, and it might be up to 40% or 30% for another grandparent. And so single-step breed plan, because we've got an understanding of the genetic relationship between animals, it accounts for the fact that you don't get exactly the same amount of DNA from each grandparent. There's a variable amount of DNA that you share, and you have variable genetic relationships with individuals in the pedigree. Okay, so that's an overview of how it works. What are the benefits of a single-step breed plan analysis? So there are two main benefits of incorporating DNA information into our single-step breed plan analysis. The first is that we can generate EBVs for animals that do not have performance data. Now, this is a range of animals. This could be animals from non-breed plan herds. And this, we've seen a situation here in Australia where some of our Brahman breeders up in Northern Australia, we don't have large numbers of animals that have EBVs. So there's a certain proportion of the population that we just have no information on their genetic merit. They, in a conventional breed plan analysis, didn't have EBVs. We're now in a situation where those people that may be interested in purchasing an animal from a herd that is a non-breed plan herd and don't have any information can get those animals genotyped, and they can get a feel for what the EBVs of that animal might be, what its genetic potential might be. And it's actually been really interesting to observe, because what we've seen over time is that some of those non-breed plan herds have started genotyping, and so they've got EBVs because they've collected a DNA sample. And what they're now doing is they're now coming in and starting to performance record as well. So that's been an interesting journey to observe. We also can generate EBVs for young animals that don't have performance data because they're not old enough to be measured for the traits. So I'm sure Boyd would have covered in his talk last month about the ages that we collect performance data for breed plan, and hopefully you'll be aware that we collect traits over a 2-year period for most animals. So young animals may not be old enough to be measured for the trait. If we can get a DNA test done, we can get EBVs generated for those animals before they're old enough to be measured for the trait. We can also do that for traits which are hard or expensive to measure. So, for example, net feed intake and methane are traits that are expensive to measure. We have got net feed intake EBVs in breed plan currently for some breeds. We do not have a methane EBV, but it is one of the research EBVs that's currently being investigated in research projects in Australia. So what we would hope there, because these are hard or expensive to measure, we're only ever going to be able to get a subset of animals that are measured. And so if we can have a good reference population of animals that have phenotypes for net feed intake or methane and also have genotypes, we can then get EBVs out further into the rest of the population within that analysis. They might not be able to be phenotyped themselves, because we've only got limited funds, for example. But if we can get some DNA taken, then we'll get more informed information on those traits that we haven't been able to measure on the whole population. That also applies to traits that are only measurable in one sex. So things like mature cow weight and female fertility are obviously only measurable in the females. And also traits that are only measurable once the animal is dead. So our classic trait list there is abattoir carcass traits. So traits that are measured in the meatworks. The next benefit is that we can get more accurate EBVs generated for animals with limited performance information. So typically, that's going to be your young animal that may have its own performance data, but it doesn't yet have progeny. And our classic example there is our 2 or our 3-year-old rising 2 or 3-year-old bull that's come up for sale for the first time. So he's been old enough to be performance recorded for all of the main breed plan traits, but he doesn't have progeny on the ground yet. So he's going to have medium accuracy EBVs. Genomics, getting single-step breed plan, getting some DNA information on him can give him a bit of a boost to his accuracy, his EBV accuracies. And the other group of animals that this is really useful for is animals that are in small or single animal contemporary groups where we don't have a large amount of animals within their mob or their group to compare them to head-to-head in the breed plan analysis. And typically, that is for smaller breeders that might only have a small number of stock on farm. So for example, over here in Australia, we've got producers with 20, 30 head, and that's all they've got on farm. So they're never going to have large contemporary groups of animals compared head to head. But also things for all producers, no matter what size herd you have, things like ET calves, because typically we see producers only doing only have a small number of animals involved in their ET programs, and also twins. Most people get some twins, but not a lot of twins each year, and they are not compared to singles. So they are animals that often end up in small contemporary groups or contemporary groups by themselves. And so in those cases, these animals are going to be helped by the fact that we can get DNA information, because we wouldn't necessarily be able to get them in good sized contemporary groups to get a lot of information from their performance information to inform their breed plan EBVs. So what all of this will do by giving us more accurate EBVs is allow you to make more informed selection decisions at younger ages than what you can do currently. And that shortens the generation interval and allows you the potential to increase your rate of genetic improvement. So what can you expect once you move to, or if you already have moved to single-step breed plan? I just wanted to take you through a case study we did a few years ago. This study is a few years old now, but it was published at a genetics conference that's held around Australia and New Zealand, and I can provide the paper if anyone is interested. But at the time that we did this study, the breed had a reference population of approximately 10,000 animals. And what we did, so that we could see what effect genomics was having on the EBVs, we did 2 test runs. We did one where DNA information was included, so a single-step breed plan evaluation, and we did another run where DNA information was excluded. So that's our conventional breed plan analysis. And it's important to note that we did that on the same data set. We didn't look at a different month. We didn't look at, say, a July analysis versus an August analysis, because we know that additional animals come in each month, additional performance data comes in each month. It was the same analysis, same animals, same performance data. It was just whether or not we had genomics included. And what we found when we did that is that average EBVs have not changed. So that was good. We were quite happy with that result. We can see if we look here across the different traits, down the different traits, the conventional breed plan average, the single-step breed plan average, you'll see that they're very, very similar. Very, very little change in what the average EBV was for that analysis. And that's good. That's what we like to see. But what did change was EBVs for an individual animal. And so what we have here is the breed plan EBVs when we don't include genomics, and the breed plan EBVs when we included genomics in our single-step breed plan evaluation. And these are young animals, so animals without progeny and without progeny. And I think they were 2-year-old animals off the top of my head. Sorry, I'd have to check the paper for you on that one, but certainly young animals, no progeny. And so what you'll see is that some animals, their EBV shifted upwards, and some animals, their EBV shifted downwards. So for example, this one here, EBV moved quite a bit. It's gone from 28, say, to plus 45. Whereas this individual started off at plus 18, and actually that might not quite line up, but he has dropped down. His EBV has decreased with the inclusion of genomics. And then if we put our sires in, we see the same pattern. So these sires are sires that were greater than 75% accuracy. And what you'll see is we still see movement. Some have gone up, some have gone down. Their EBVs have changed, but we don't see such an extreme change. So they're closer to this line than the younger animals were. So what we found is that when we have included genomics data, some animals have had EBVs increase, some animals have had EBVs decrease, but we don't see a skew in direction. Some go up, some go down. That's good. That's what we want to see. We don't want to see a systematic error where all the EBVs go up or all the EBVs go down. We want to see it's spread where they're moving in both directions. And what we also saw is that animals with lower EBV accuracies have greater levels of EBV change than those with higher EBV accuracies. And that's not unexpected. Genomics is another source of information. And so when you add additional information into the calculation of breed plan EBVs, animals with not a lot of data behind them, so lower EBV accuracies, are more likely to change when you add additional information. Animals that have lots of data, so proven sires with high EBV accuracy, if you add some extra performance data, they're not likely to move as much because they've already got quite a lot of information behind them. So that wasn't unexpected. We were very pleased to see that happen. The next thing we saw is that variation in EBVs has increased. So we see more spread with single-step breed plan. And so this is for 200-day weight. And you'll see that at this top end, we get animals with higher EBVs than they had under the conventional breed plan. And it's hard to see on this one, but down this end here, animals that had lower EBVs than under conventional breed plan. And that's good because that means that single-step breed plan is helping us to better identify animals at the extremes. And that's really helpful because those ones that are up the top end are usually the ones that we want to use for breeding programs. But it's also important that we are identifying those at the bottom end because they're typically the ones that we want to cull from the breeding program and don't want to perpetuate through to the next generation. The last thing we observed is that EBV accuracy has changed. So what we see here, EBV accuracy without genomics and EBV accuracy with single-step breed plan. And this is the change in EBV accuracy. And so what you'll see is these lowly accurate animals, they had low starting accuracies, they've gone up in accuracy quite substantially when we've added genomics in. But if we look at these high accuracy animals, these ones up here that had between 80 and 99% accuracy already, we're only seeing small increases, maybe 1 to 2% in EBV accuracy when we add the genomics in. And that's because of what I was saying just before. If you add a piece of data to an animal that has a low EBV accuracy, that data piece is going to typically have a large effect and the accuracy will jump up. But if you've got an animal that has lots of data already and you add one more bit of data, he's only going to jump up in accuracy a little bit. And so we see that pattern when we look, in this case, for 200-day weight. But if we go and look at other traits, we see the same pattern again. So here we've got days to calving, and you can see that these lowly accurate animals, we see an increase in accuracy when we add genomics in, but these highly accurate animals up here, only a small jump in accuracy. And so what we found is that the change in EBV accuracy is not uniform across animals. Less accurate animals, animals with lower starting EBV accuracies, show bigger increases in EBV accuracy when we add genomics than animals that started with a high EBV accuracy, and that is consistent across traits. What isn't consistent is how much jump we see in the EBV accuracy. Some traits, we do get a greater lift in accuracy when genomics is included than we do for others. So a good example there, we were seeing more of a lift for 200-day weight for those low accuracy animals than we were seeing for days to calving. And that is because the lift in EBV accuracy is not just influenced by the heritability of the trait, so how much of that trait, the variation in that trait is explained by genetics, but also by the number of animals in the reference population for the trait. So that's the number of animals with genotypes and performance data. And we also then went and had a look at EBV accuracy across different breeds. And so in this case, there are 3 traits here that got looked at. We've got 3 different breeds, and it was the average increase in EBV accuracy once we added genomics for animals that had a starting EBV accuracy of 30%. So you can see for 200-day weight, breed 1, breed 2, and breed 3, the amount on average that a 30% prior accuracy would rise by varied from 15 to 23%. If we look at days to calving, this breed doesn't have days to calving, but breed 1, the average lift was 3%. So on average, animals that started at 30% accuracy went to 33% accuracy, whereas for this breed, animals that started at 30% accuracy went to 40% accuracy. And for marbling, we saw that vary as well, so from 8% up to 15%. And so really what this is showing us is that different breeds have different compositions of their reference populations, and the difference is being driven by how many animals we have in that reference population for that trait. So I'll just pause there for the moment, Mario. Have we had any questions come in?
Thank you so much, Katrina. There's been nothing on the chat group, just someone supporting our Stockman school saying it's the best. I agree, but I'm happy to take questions. Do people want to pose them here or type them up? A very comprehensive, excellent presentation. Thank you, Katrina.
Okay, well, if we've got no questions come in, I'll keep going. But if you do think of questions while I'm going through the next bit, just type them in and we'll pause again at the end.
Excellent.
So what I just wanted to go through now is considerations. So 2 main considerations I wanted to discuss: should you keep collecting performance data, and which animals should you consider for genotyping? So as I've hopefully alluded to already, the phenotypes, the performance data is really, really vital for the ongoing success of genomics, of single-step breed plan. So Professor Mike Coffey at the Roslin Institute in the UK said this a few years ago: in the era of genomics, phenotype is king. And that's because our reference population is vital to the success of single-step breed plan. Single-step is going to work best when the current population is closely related to the reference population, and that means that therefore our reference population will need to be updated over time. We need to constantly have animals with both phenotypes and genotypes coming into the analysis going forward. And I think it's important to note that we want phenotypes for a range of traits. Obviously, some traits are a little easier to collect than others. It's easy to collect weights, for example, but we really want phenotypes across the spectrum of traits, all of those traits we're trying to make genetic improvement in. So we do want our birth weights coming in. We do want our live weights coming in. We want ultrasound scanning, scrotals, female fertility, net feed intake, carcass attributes. And I've put this one in here because I'm sure that over time we're going to see new traits coming into the breed plan analysis. And this one I put in because in Northern Australia, we're seeing some research go in to things like tick scores and buffalo fly resistance. And so I think we'll see health traits come into the analysis as well. Those animals, those populations that are getting tested for some of these hard to measure traits in particular, or new health traits going forward, those are the sorts of animals we want a full suite of phenotypes and performance information collected on. And we want those ones to be genotyped because they're going to be really informative for your reference population at a breed level. At an individual herd and animal level, I think it's important to recognise that genomics single-step breed plan will likely give your EBV accuracy a bit of a boost, as we saw in the worked example earlier, but it's unlikely to move unlikely to move young animals with lower accuracy EBVs right up into that high EBV accuracy, so that 80 to 90% accuracy territory. It's going to give young animals a boost, but it's not going to move them up to proven sire levels. And so I would personally be considering DNA testing to be an additional source of information rather than the only source of information that you collect. It's helping you, but it's certainly not replacing performance data and the need to collect performance data on your animals. And I think another point that we often don't think about is that any animal that has both performance data and genotypes is going to become part of the reference population. And so therefore, if you have animals in your herd that have performance data and they have genotypes, you're part of the reference population. That makes you closely related to the reference population, and that is beneficial to you going forward, because as you bring their sons and daughters of those animals that you have with performance and data and genotypes, they're closely related to those animals in the reference population. That's going to help them through the single-step breed plan analysis in the future. And then just wanted to cover which animals should you genotype. So really when we're thinking about, right, which animals should I genotype, it does depend on what you want genotype results for. Do you want them for single-step breed plan? Do you want them for parent verification? Do you want them for management of genetic conditions and or qualitative traits? Or most usually a combination of the above. So depending on what you're trying to do, the answer of which animals should you genotype will vary. But what I did want to say was that here in Australia, as we've made single-step breed plan available for different breeds, we have certainly seen a big uptick in the number of animals that are being genotyped. So I've got 3 breeds here for you. This is cumulative genotypes across calendar year, so it is not calving year. It is here, for example, the genotypes that came in throughout 2017, and then by the end of 2018, how many we had. And so you can see across time, we're seeing more and more and more animals being genotyped. And that is consistent across those 3 breeds. So anecdotally, what I think we've seen is a shift from producers who are just doing their sires or just doing their sale bulls through to people that are genotyping their female breeder herd. And so just to give you a little bit of history, when we first started talking about single-step breed plan and getting genomics rolled out for certain breeds, the way we approached it, because that reference population needs to be representative of the breed as a whole, we did recommend, and I spent quite a bit of time working with individual breed societies to find animals that were well-used sires that had their own performance data or progeny with performance data that were representative and widely used throughout the breeds. So historically, the first breeds that got turned on, they had a lot of historically important animals. They didn't have a lot of young animals that had been done. So it tended to be older sires. And then Certainly, over here, people have moved to doing parent verification for their cell balls. And so because the DNA labs are offering bundles where they put a range of tests together, so PV, genomics for single-step breed plan plus genetic conditions, we saw some of those cell balls coming in with genomics, and they were certainly being done at more high levels than females. But more recently, I'm starting to talk to producers who are doing their entire female cohort. And so it's a consideration, but we know that the cost of genotyping the entire female herd can be prohibitive, particularly if you try and do it in a single hit. So one way that we're seeing producers do that is to build up their females genotyped over time by doing the heifers each year. And so the question then becomes, well, should I do the keepers? Should I do the maybes? Should I do the culls? And this comes back to, why are you genotyping? If you are genotyping for selection decisions, you're not going to do the culls, because the culls, no matter what their EBVs say, no matter what the genomics says, you're not going to keep them. So you're not going to do the culls. If you're definitely keeping an animal, you're probably not going to change your mind if you genotype her. But the maybes are important there. The ones that you're going, will I keep her? Will I not keep her? She's the one you're making the selection decision on. She's the one that you would be genotyping to see whether or not you're going to keep her. But if you are genotyping from the point of view of getting your females done across the entire herd, the ones that you're going to do are the keepers and the maybes. So that over time, what we would recommend, and you can see here in this example, is you do your replacement heifers in year 1, and then the next year you do your replacement heifers. These ones were done the year before. Year 3, you do the replacement heifers. You've already got the 2 and 3-year-old cows done. Year 4, you do your replacement heifers again. You've got your 2, 3, and 4-year-old cows already done, and you cycle through that way. Now, obviously, it's going to depend on your cast for age, how many years it takes you to get there, but that's a way you can do if you want to build up and start doing your females. Start with your replacement heifers, do them each year, and that will build the number of females you have genotyped in your herd. Now, the reason we recommend starting with the replacement heifers rather than the older cows is because the replacement heifers are going to be in your herd for a longer period of time generally than your older cows, because hopefully you keep them through their breeding and productive life. And also, if you're looking, for example, to start doing full parentage verification, they're going to have multiple years, hopefully, of calves ahead of them. And so you're going to get the best bang for buck by doing them, because they're going to be there influencing the genetics of your herd for more years going forward than an older cow that might only have 1 or 2 more calves for you. So for those of you that are interested, we do have some more information in our Case for Genotyping Females technical note. It's available via the Breed Plan website. It is under the Extension Services Resources Technical Notes area, and you can access that directly, or I believe the link to the Breed Plan website is also available via the LRF website. And then just to finish up in our last few minutes, future directions. So as I said, we've got 17 single-step breed plan analyses, including 3 for breed societies across Southern Africa, Hereford, Brahman and Limousin. But implementing single-step breed plan analyses for additional evaluations remains a key priority for our breed plan team going forward. The challenge many breed societies have had over, and this is not unique to any particular country or region, it is a challenge for all breed societies, is that we do need a reference population, so animals with phenotypes and genotypes, which is representative of the current population. And so for most breeds that have been doing a lot of performance recording, finding animals with performance records isn't difficult. What is difficult is finding animals with genotypes. And so that's been a challenge for a number of breeds as we look to implement single-step breed plan. Our other thing that I wanted to flag is our Breed Plan Select. So this is a new product that ABRI has been working on. and it is a DNA-driven genetic evaluation for commercial cattle. So it doesn't need trait or pedigree data. It is a DNA test. It's not suitable for seed stock. It is aimed at commercial cattle, and it uses prediction equations derived from single-step breed plan. And where that's useful is if you think about your commercial clients. Often commercial clients have a good understanding of the genetic merit of their bulls that they're purchasing, because they're purchasing from seed stock. Those bulls have EBVs. We have a feel for where they fit, but often they don't have a feel for where their commercial females are sitting relative to the breed. So this is a photo here of some commercial cattle at a friend of mine's. We would have no idea what the genetic merit of those commercial cows is. Where something like Breed Plan Select is useful is that you can do a DNA test and get a feel for where those commercial cattle sit relative to the seed stock population or the breed, and that allows you to make more informed decisions in your bull purchasing and also your female selection. So that is a product that is being rolled out in conjunction with Hereford in Australia to start with, but is certainly something that I expect we'll see become more popular and be rolled out further with other breeds that have single-step breed plan over time. So with that,